Okay, so this video is an intro into our very first unit, our very last unit, called continuous probability distributions. Okay, continuous probability distributions are the same thing as our discrete probability distributions from last unit. They're distributions of probability. In other words, they see all of the different outcomes and how they're spread out. If you take the entire distribution, it all adds up to be 1 or 100% for probability, and all the individual pieces are all accounted for, okay, in a distribution. There are patterns and things like that that exist, and we notice those with the binomial and hypergeometric, and even to some extent, even in the patterns that existed in individual probability events. For continuous probability distributions, we're looking at either repeated trials or we're looking at individual outcomes. And really, when you get a final answer with continuous probability distributions, it actually ends up being two things. One, it would be the probability of an individual event occurring, whether it's multiple successes or one success in one event. Or you will get the frequency of those particular things, those particular criteria that would be considered a success, the frequency of them existing in the population. So they're one and the same. So try to remember the probabilities of marriage between relative frequency and probability, or the basic likelihood of something happening. To start with, rather than doing worked examples, I'm just going to go over the notes, because really that's all it is going over notes. And then afterwards we'll work towards doing some worked examples. There aren't really a lot in this particular section. There's only 3 homework questions. Most people mess up question number 6, so they want me to take it up. But either way, I'll give you an example, hopefully that's tangible and able for you to do it. Okay, so first of all, continuous probability distributions and discrete probability distributions, as I said, they have a lot in common because they're probability distributions. Continuous just means that our random variable x is continuous. Okay, so it could be looking at a measurement like mass, okay, where you can have any particular value within a spectrum of what's acceptable, or a measurement like time, or a measurement like height, or things like that. So it's actually a fairly common measurement for us to encounter. Discrete outcomes can exist, but they don't always exist. Very often, statistically, we want to look at continuous outcomes. So of course, probability distributions for continuous variables need to be developed as well. Okay. Again, we're dealing with the same idea, the random variable x. And the random variable x, of course, is a particular outcome or amount of outcomes that exist. So in other words, we can view them as successes, or we can view them as individual outcomes. The probability of an 8, or the probability of getting an 8 7 times out of 10, or something like that. Okay, and very often this does involve repeated events, so it's something to keep in mind. For discrete probability distributions, they tend to be either discrete or categorical in nature. They can be categorical variables in that we're looking at a number of successes of those categorical variables coming up, like the number of times a red Smartie comes up, or whatever it may be in a handful of 5. But heading towards it, one thing to keep in mind for all of this is that whether we have a uniform distribution, this would have been basically for our first section on the intro, where we're doing individual events. This is rolling a single 6-sided die. And you can, of course, see discrete outcomes with bars that are separate or separated from each other, like they should be for a discrete bar graph. For a binomial distribution, this is an example of a binomial distribution of heads and tails, okay, where in this case, number of tails is a success, and we're looking for the number of tails that occur in 10 tosses. Okay, so 0 all the way to 10. For a geometric distribution, that's actually from a section that we don't usually cover that much anymore. It's not really in the curriculum anymore, because really we're looking at a binomial versus a hypergeometric for 2 different situations. It's a very common distribution, a geometric or exponential distribution. So it's good to see, but, well, we didn't cover that. But that would be a situation where we have a very specific type of expected value. And then a hypergeometric distribution. Again, binomial for independent events and repeated trials for independent events, and hypergeometric for repeated trials that are dependent events. Here would be the probability distribution showing the number of women in a 10-person group chosen from a class of 10 men and 10 women. Okay, so there's my success pool, women, my failure pool, men, and I'm choosing 10 people from that group, okay, a subgroup. All right, just like I normally do, I do some sampling. Okay, and in that case, of course, I can get from 0 all the way through till 10 women out of 10. okay, and their probabilities associated with that. Again, if you notice all of these, the bars are separate, but more importantly, and this is probably something you wouldn't notice at a first glance unless you did the math, that all of these, even this very small probability for any of these, all of these always add up to 1. And this is something that we need to take home with us as we're working through continuous probability distributions. All probabilities in a distribution always add up to 1. Even in a geometric distribution, which technically goes on forever, it approximates 1, and it certainly approaches 1. Okay, but for all of these distributions, they always add up to 1. The easiest way for you to see it is for 1, 2, 3, 4, 5, 6, for a single outcome of rolling a single 6-sided die. You're going to notice the probability is 0.16, it's actually 0.166. So if you add 1, 2, 3, 4, 5, 6 of those, it's going to add up to 1. The rest of these is a little bit more difficult to see, and you're going to have to trust me. But you can go ahead and do a distribution for any of these trials, and you'll see it. Okay, you'll see that it adds up to 1. Okay, so that's something important. And of course, I've got that highlighted in green here as well. To go further, okay, the whole idea that a continuous distribution or a discrete distribution should have the same principles. One principle that's in common is that a continuous distribution also always adds up to 1. Okay, and we're modeling the situation again. This is just talking about modeling it for continuous variables rather than discrete variables. Okay, and in summary, a few characteristics that are really important for you at this level. Continuous probability distribution has the same properties as a discrete probability distribution. The sum of all outcomes is 1, and each outcome does have its own distinct probability. Okay, but the difference is that the number of possible outcomes that exist for a continuous probability distribution is basically infinite. So the individual probability of an individual outcome is so small that the amount is basically negligible. Really what we're going to be looking at largely in here is we're going to be looking at ranges of probability. Greater thans, less thans, maybe even some equal to values, but the equal to values are for discrete variables. Again, that's a lot at once, but the whole take-home message is still same idea. Sum of all outcomes is equal to 1, and each particular value has its own individual probability. So that still is something that's important for us to understand. Okay. Now, when we graph or show a table for continuous distribution of probability, we have to do all values in corresponding bars, or in this case, they would be histogram bars, corresponding to those values. So that means the bar gets really, 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 really skinny, really, really, really small. Okay, because it doesn't occupy, like, for example, a width of 1. If we're talking about, I don't know, number of successes, you could have 1 or 2 or 3. So each bar has a width of 1 for a discrete outcome. For a continuous outcome, the probability of, I don't know, 45 grams is pretty small because the bar is infinitesimally small. In fact, it's not even a bar. Really what it is it's a point. Okay, and that's an important idea. Okay, so one way in which we deal with this, a little bit lower down here, is when we look at a discrete outcome or a discrete distribution. This is a binomial distribution, which is very often used in concert with a normal distribution, which is one of the distributions we're going to talk about. So rather than having bars, we have a function. Okay, because remember, those bars are so skinny that you can't even really give them thickness. And if you can't give them thickness, then what ends up happening is they become this infinitesimally skinny line that really only has a point. And that point that exists, of course, creates every single point for this continuous function. Okay, and for those of you guys who did advanced functions, you know about continuous and discontinuous functions. Okay, where they have holes and things like that. No holes here. Okay, there's holes here, lots of holes here, no holes here. Okay, so when you're looking into functions, we have discontinuous and continuous functions. This is a continuous function for continuous variables. Okay, so that's something that's really important. So one thing that we don't do is we don't do bars, we do a function. We do a sketch, a curve, if you will. In this case, it kind of looks a little bit quadratic for a bit, and then it kind of tails off asymptotically, okay, which is obvious because you can have a negative probability. Okay, so there we go. And more considerations, more notes. The probability of a range of values is easily calculable. Okay, in a continuous distribution. Okay, what we actually do is we call it a probability density. Okay, in other words, how much probability is in that little range or in that area. Kind of like density is, mass per unit volume. Well, the mass here is the probability, and the volume is kind of like the width of the range. So how much of that is in there? And it's really a proportion of the entire function of 1. So that's really what a continuous distribution is, and that's the number 2 criterion. It's a probability density function. If we want to figure out the probability for a range for a discrete distribution, and we had lots of questions like this. Let's say we want to know the probability of x as being less than 3. Okay, I don't know. Let's say we, I don't know, roll a die 10 times, and a success is a 4. Okay, well, what's the probability of getting less than 3 4s when I roll that die 10 times? Okay, so that would be a probability of less than 3. Now we know that we can do that by figuring out the probability of 0 3s, 1 3s, 2 3s. And of course, it's less than 3, so it doesn't include 3. So it's 1, 2, and 0, 1, 2, 0, 1, and 2. Okay, and then what we do is we add them all up. And the reason why we can do that is because it's discrete. We can calculate it. Okay, we can use our continuous probability, use our binomial distribution formula for rolling a die, or for sampling people from a group. Use our hypergeometric distribution. We can get the probability for 0, get it for 1, get it for 2, add them all up. You have that in examples from your last unit, as well as homework questions that you've done. Okay, but what we don't realize is the width of this probability is 1. The width of this probability is 1. And the width of this probability is 1 because it's a continuous function. Or sorry, discrete relationship. So what happens is, whatever area we get for this, we really should be multiplying it by 1. We should be, by doing a probability density function, be measuring an area under the curve, or an area of the bar. And the area of the bar is a length times width. Well, the length is really the probability. It's how tall the bar is. The width is, so this is sort of my length, that's my probability. And then the width is going to be 1. Well, if you take any probability and you multiply by 1, it's just a probability. So that's what we've been doing all the way along. We've still been doing a probability density function. What we haven't realized is that this extends into a continuous distribution of probability. Okay? And more important, for continuous probability distribution, we do tend to look for a range of values. What's the probability of a bag of chips weighing less than 45 grams? What's the probability of a bag of chips weighing more than 45 grams? What's the probability of a bag of chips weighing between 40 and 50 grams? Okay, that's still a range rather than a specific value. Okay, and of course it makes it difficult for us to do the probability of x is equal to 0 for a continuous distribution, a probability of x is equal to 45 grams for a bag of chips. But doing ranges, a continuous distribution is beautiful for that. Third criteria that's important is the probability of individual values of x in a continuous probability distribution can be calculated by using a fairly complicated function. You can see it in your book if you want to. Okay, for it, depending on what it is. And the example that we're going to be using today, we would be able to calculate the probability for an individual occurrence, but the area would be so infinitesimally small that it would be difficult for us to do. So we're only really going to be calculating ranges, and largely for continuous variables, we're only going to be doing ranges. It doesn't mean that you can't make that range be infinitesimally small. If you want to find out the probability of having a bag of chips that's 45 grams, that's fine. You can get really close to approximating it by figuring out the probability of a range between 45.000000001 and 44.9999999. And that range in there, in essence, is going to be what 45 is in all realistic outcomes. But, okay, again, we want to keep the idea in mind that for a continuous probability distribution, we do tend to calculate ranges. Okay, so in summary, overall, the probability distribution of a continuous random variable x forms a line or a function rather than a pattern of bars on a graph. Not too crazy. It's basically like a relative frequency. And remember, we called these at the beginning of the year, really way back then, a polygon. Okay, rather than drawing a bunch of bars, we connected the midpoints of all the different groupings. In this case, the groupings all mash together into a histogram, and that histogram can have a polygon associated with it. And that's really what we do, a frequency polygon, relative frequency polygon. And then more importantly, for our calculation purposes, the area under that curve represents the probability of that range of outcomes, or the range of our random variable x. Okay, so now let's get to some examples. Okay, we start with something simple to calculate the area of, and therefore the probability of, and that is something called the uniform distribution of probability. We've already done a uniform distribution of probability for a discrete variable when we looked at the rolling of a single six-sided die. But now we're looking for the uniform distribution of a continuous variable, which is a little bit more rare, but we're going to keep it simple, state a simple principle, and it's an underlying assumption. Remember that eventually we're going to get to the point, not this year, but when you get into statistics, where you're going to do hypothesis testing. So you're going to test what's happening in real life compared to this. If it has this rough overall outcome, you can approximate it very easily. If it doesn't have this rough overall shape, then you move away from that. And then you'll do things like measuring skew for a normal distribution and all kinds of craziness when you get your statistics in university. But for now, we're going to keep it simple. We're just going to say, hey, let's just go with this. Okay, so here's an example. I totally made this up. The cashier at a bulk barn says the probability of a mass of Smarties sampled by people who go into the classroom, is uniformly distributed between 20 grams and 500 grams, meaning that the probability of getting anything between 20 grams and 500 grams is pretty much equal. People just take a scoop or multiple scoops or little bits or whatever, and it always ends up being between those two values, an equal probability between them. Never had anything more than 500 grams, never had anything less than 20 grams, which is not very probable, but 20 grams is not much. When you go into the bulk barn, you're usually going for quantity, and 500 grams, maybe it's too big for the bag and it bursts a bag. Whatever, I don't know, whatever. I've just made this up. So first it says sketch a well-labeled graph showing the distribution of masses. Okay, so if it's a uniform distribution, okay, it even says here, uniformly distributed. Okay, now this is where I get to the worked examples. So here is our blank. Give me a second here. Here's our blank. Okay, and of course you've got beautiful worked examples here. So in your notes, you've got this all worked out nice and pretty. So just follow as we go along. Okay, to sketch a well-labeled graph, you may think, oh, it's like sketching a distribution. It's really easy. It's so boring. Okay, true. Okay, my random variable x is mass. Okay, that's my random variable x, and this is of course my probability. It's always my probability for a probability distribution. Okay, it goes from 20 all the way to 500. My scale here, of course, is awful. All right, but you don't really have to label it that perfectly. You can if you want, and go from there. But I'm not going to for the purposes of what we're going to do here. And we know it's a uniform distribution. That should be straight across. For those of you guys who know I can barely draw a straight line half the time. But it should have the same probability all the way across. Whatever that probability is right here. Okay, so maybe it's 10%, maybe it's 1,000%, or not 1,000%, 15%, maybe it's 20%. I don't know. In fact, I'm going to calculate in a second. Okay, so between the range, this is it. Between the range of here and here, this is it. And this is a really important idea. Because remember, to figure the probability of a range, it's going to be an area, and that's an important idea. Okay, so this is an important idea to take home. Probability equals an area under the curve. That's really important. Okay, so if I want to figure out the probability between 20 and 500, I would actually have to calculate the area of this function. For those of you guys who are physicists, you've done a lot of this. Okay, calculating area under the curves. To find displacement under a velocity time graph, or to find average velocity under I think acceleration time graph. That's where my physics leaves me. I have to ask Mr. Wallman or one of our physics teachers. Either way, you've done areas under curves, okay? And of course, later on, you're going to do calculus and integration. Integration is area under a curve as well, and then you can rotate it and do all kinds of craziness. Let's keep it simple. Area. Now, for this, we can calculate the area. The reason why we can calculate the area is it's a rectangle. Okay, area of a rectangle is not difficult to do. So keeping that idea in mind, we really have a length and a width. That's the formula. Right? So in this case, we don't know what this probability is, and it would be useful for us to have a meaningful graph to know what that probability is. But there's a few things that we do know. We know that probability is area under the curve. Okay? We also know that the probability of this entire range from 20 to 500, from 20 to 500, is going to equal 1. I know that. Because it's everything. It's the whole distribution. Nothing smaller, nothing bigger, that's it. But we can use this to actually figure it out. And you're like, what? That's crazy. Okay, so let's go with this. So if the probability between 20 to 500 is 1, or 100% if you want to do it as percentages, but I recommend you do it as a decimal, that's also equal to the area under that whole curve. Now my area is going to be my length times my width. Okay, let's say we make the length, although most people see this as a height, let's say we make that arbitrary amount the length. Okay, well that goes from 0 all the way up to my probability. So from 0 to my probability, sorry, let me write down LW. So from 0 to my probability minus 0